here we are to talk about arc length and curvature in the context of 3D. There's a lot that goes into this and not so many examples, just a lot more talking. So I'm going to try to keep it to a minimum on the talking and just let the work kind of breathe and prove itself. So let's do this. 13.3 is probably the heaviest section in this whole thing. It is tricky. I've split it into two pieces. This is the flip piece. We'll do the other piece in class, and then kind of have a holistic view and some practice on it. All right, if I want to find curve length, remember with me, if I want to find the length of this piece of curve from here to here, I can approximate it with that and actually draw a right triangle in here. Let me zoom in. I would call this side my change in x, and I would call this side my change in y. I recognize it as a right triangle, so if I want to find the length of that third side, it would look like this. Right? But the thing is, I want the whole length of the curve from A to B. Well, in order to do that, I would have to integrate. That integral would make infinite little triangles, add up all of these hypotenuses all the way from A to B. Infinite hypotenuses on infinite little right triangles, a beautiful infinite summation where I just keep building triangles and triangles and triangles and triangles and triangles and adding up all those hypotenuses. Now, change in x, change in y. Now, back in Calc 2, you had dx, dx, and dy, dx, because as x changes, and as y changes, it's based on x, because x is that independent. We know that dx, dx is just 1. And so that's where you got that formula in Calc 2, 1 plus f prime squared, because this is f prime, and dx, dx is just 1, because x changes as x changes. We move it to parametric now, where x is based on t, y is based on t. So this becomes dx dt squared plus dy dt squared. Throw in some parentheses. And then I square root and I integrate that thing. And now we expand it to 3D, so it's harder to see why the 3D Pythag would work, but just believe me that this is, instead of Pythag, maybe you think of it as the distance formula. The distance change in x and y and z based on t, all squared for that distance formula, change in x, change in y, change in z. Well, when it's a vector-defined function, I know that my function is f of t for the I direction, g of t for the j direction, and h of t for the k direction, and so that's why I get these three. And so I could see this as magnitude. These should all have little primes, huh? Prime, prime, prime. It would be the magnitude of all of these derivatives. And so that's what curve length ends up being. The integral of the magnitude of the derivative of my vector-defined function. Whew. A lot of language there for a clean and simple idea. Let's do this one together. Again, my derivative here, r prime of t, would be negative sine t I plus cos tj plus 1k. When I take that magnitude to get that curve length as seen in this formula, zoom out a little bit. When I take that magnitude, I would get sine squared plus cosine squared, right? Because I'm squaring the derivative components, plus 1 squared. Well, sine squared plus cosine squared is 1, and 1 squared is 1. So that value is just equal to 2, square root 2 in this case. Well, now that becomes the inner portion of my integral, and in this case I'm going between these 2 points. We need to pause and take a moment to think, well, what are my bounds on t? I know my integrand will be square root 2. I know I'm going dt, but what is the change in time from this coordinate to that coordinate? A little bit dicey because I don't see my x change, I don't see my y change, but I do see my z change. And that z is based in t. So here, t is equal to 0, and here t is equal to 2 pi. So those become the bounds on my integral. I find my antiderivative, rad 2 times t, and I evaluate that antiderivative from 0 to 2 pi. I'll get square root of 2 times 2 pi minus 0. So that is my final answer. This is the curve length of the helix from t equals 0 to t equals 2 pi, or from this coordinate to that coordinate, is that value, whatever that number ends up being. I prefer the exact answer. But one thing we have to be mindful of is, like, is this thing continuous? Is this thing continuous? Because I cannot take this integral, I cannot measure the curve length if there's a break in my curve, right? If it went like this, how would I find that curve length? I would have to take each piece and add them up individually. Yes, all three components are. Cos t is continuous. Sine t is continuous. T is continuous. So all three functions are continuous. Also continuous in that direction. Here we go. Now we're getting into the fun part. What if I took that same concept and said, hey, instead of talking about curve length, instead of plugging in time and saying, hey, how far have I traveled on the curve based on time, what if I flip this around? Let's pause for a moment. What if I flip this around? I look at this bottom box. So imagine, instead of my perspective being on time passing, it's like distance elapsed, like my odometer. We're going to name S this distance. Well, we do need to set speed equal to 1 just to make sure that our original function is normalized, so that passing of distance and time have a more direct relationship because speed is constant. If that confused you, just set it on the side. And we will parameterize our original equation. So what we're going to do is define curve length as that same integral we did above. Notice I switched out some things here to be technically correct. This is u, and this is u, and these are u, because I know that I'm going to plug in this t at the very end when I evaluate this integral. And so that's why t becomes the input for my curve length. So that would mean that ds dt, I'm taking a derivative of this with respect to t, would be the same as the derivative of this with respect to t, which would just become r prime of t. Right? Fundamental theorem of calculus. The antiderivative of the integral is the original function or inner function itself. Well, the other thing that I would have to be mindful of here is that, like, let's think of how it applies to that previous question here. What we found is that the curve length was equal to the square root of 2 times time. Well, if I wanted to reparameterize the original function, I would just have to find what t is equal to, s over square root 2. And now that original function from my example above, instead of being rt, it would be r of s. And I would get cosine of s over rad 2i, instead of the original, which was cos ti. The next one was sine tj. Well, based on this relationship, that would become sine s over square root 2j. And last but not least, this k direction, which is just tk, was the original. Tk would become s over square root of 2k. A simple substitution, because of course we chose a simpler example for the first one on purpose, but now instead of saying, well, where am I when time equals 5? No. I could say, where am I when I've walked blank distance? Like, where would I be if I walked 10 miles on this line? I could plug in 10, 10, 10, and I would have my location, IJK, the 3 directions. And like it says down here, notice curvature and torsion are independent of speed. So that's why we set that speed equal to 1. Again, it helps us normalize this stuff. It takes away some of the, how do you say, the yucky realities of physics kind of get washed over when we force speed to be equal to 1. Flip this over and look at the back, folks. Now, just a straight up example. Reparameterize this thing with respect to arc length. So I start with r of t. I want to end with r of s. Well, with respect to arc length from the initial point t equals 0. A little bit helpful there, but let's see what it ends up being. I need to get r prime. In fact, I need to get the magnitude of r prime, but we'll get there next. The derivative of r gives me 3 cos t plus 3 cos t I direction, 4 j direction, negative 3 sine t k direction. Okay? And when I take that magnitude of r prime, I would get square root 9 cos squared t plus 16 plus 9 sine squared t. This is not an accident, it keeps happening this way. 9 cos squared plus 9 sine squared is just 9, plus 16 is square root of 25 is just 5. So when I know that curve length s, or L on the previous page, is equal to the integral from 0 to some time of 5 dt. I know this is a little improper for me to put this t up here. I apologize. But I'm doing it for our first example so it makes sense. This is going to be 5t and nothing. Like, even if I took away these bounds, it would be 5t plus c minus 0 plus c. The c's would cancel. I'd just be left with 5t. So if s is equal to 5t, that means t equals s over 5. And now I can reparameterize that function. R of s is 3 sine of not t, but s over 5 I, plus 4 not t, s over 5 j, plus, I guess I should write, ooh, I got a little bit lost there, sorry about that, plus 3 cosine of s divided by 5k. And that becomes my reparameterization. Helpful, applied in some formulas in some places, a bit unique. And also what I'd say is, like, please make sure you understand this. Now that I reparameterized, I'm not talking about RT anymore. R of 3. R of 3 means my location after 3 units of travel. That means I'm sitting on my curve, like one of these, and I walk a distance of 3. My odometer hits 3, and I get to this moment and I say, where the heck am I? X, Y, Z. Where the heck am I? J, K. That's what this calculation does. Instead of being based on time, it's based on distance. Now, it's our job to talk about curvature. Curvature is a bit complicated. We're going to define it. We're going to do some curvatures, and then when you guys come into class, we'll contextualize it and have it make a lot more sense as we finish out the second half of this lesson. Curvature is this fancy K. And if you imagine, on my curve, my 3D curve, curvature is how that tangent function, t, changes. If there's no curvature, that t never changes. But if that t does change, it's not going to change with respect to time, it's going to change with respect to curve length. So it's how much is my tangent changing, dt, with respect to s. How far along my curve, how far along my arc length am I going? So, if you have, which is what we've done in the past, sorry it lagged for a second, that means dt dt would have to be dt ds times ds dt. Well, if I know that dt ds is, sorry, if dt ds is what I'm trying to solve for, and I know these two things are equal, I would just kind of divide this ds dt over. All right. But we also know that this ds dt is what we defined on the front side. Just that magnitude. So, if I kind of put it all together, I have dt dt, kind of funny sounding, but I would just call that probably t prime. And then ds dt is this thing. And a curvature is not a vector. Curvature is a scalar quantity. So it's the magnitude of the change of the tangent divided by the magnitude of the derivative. But then we make this jump to this formula. And I'll have a separate link with a QR code proving this formula. For now, just take it for granted, because honestly, most of the time we are not going to be doing this calculation because it takes so much time to build t and then build t prime and then take the magnitude. There's just lots of magnitudes and things. It's much quicker to go first derivative, second derivative, cross them, magnitude them. First derivative, cube it. As I said, you'll see in that separate link how that goes. Let's find the curvature. Let's find this calculation, r prime, r double prime, of this guy at the general point as well as at this moment. And again, we won't know exactly what that value means yet, but I promise we'll get there. R prime is pretty quick. 1, 2t, 3t squared. R double prime, also pretty quick. 0, 2, 6t. Right? Nice and fast derivatives. I'm going to cross these two things. R prime cross R double prime. Forgive me for starting to lose a little bit of notation here. 1, 2t, 3t squared, 0, 2, 6t. Okay, y'all know how to do a cross product. Let's do that cross product. 12t squared minus 6t squared I minus 6t j plus 2k. Nice and clean. And I'm going to take this magnitude and I'm going to divide it by the magnitude of this thing cubed. This is going to get yucky for a moment. It really is. This is going to get yucky for a moment. Let's take this thing's magnitude for the general point. This makes a 6t squared, so that would be 36t to the fourth. This would be 36t squared, and this would just be 4. I'm not even so worried about factoring it, it's simplifying it, right? When it just says at a general point, I just need t, because these general points will be generated by t values. Then I divide it by, again, this magnitude cubed. So this magnitude would be 1 plus 4t squared plus 9t to the fourth cubed. This is my general curvature at any moment along this twisted, I forgot the name of it. Oh well. Twisted beautiful curve. Twisted cubic. Well, it says do this at a general point. Done. Now do it at 1, 1, 1. Well, at 1, 1, 1, I know that t equals 1. When at t equals 1, my curvature, again, would turn into this. 36 plus 9 over square root of 1 plus 4 plus 9. Neither of those numbers are nice. Neither of these things simplify very well. But in case you're, oops, did I write 9 instead of 4? Yep. Square root of 80 divided by square root, square root 76 divided by square root 13. Not a nice number. We'll understand what this number means when you come into class next. Just understand how I calculate curvature using this formula. Now, we have a special different formula when things are f of x. When things are not vector defined functions and they're just regular defined functions, I can find the curvature. And just think about it this way. When I'm doing this numerator, which is r prime cross r double prime, on a function like this, you could really think that t prime, kind of from this guy, t prime is the same as r double prime is the same as f double prime. And so that's where you see that numerator comes from. Then my denominator is just kind of curve length, isn't it? The bottom ds dt is curve length. But it's like the antiderivative of curve length, 3/2. Or you could view it as, hey, this thing is curve length cubed. Curve length in Calc 2 was this, and I cubed it, 3/2 power. If you don't believe me on either of those things, just use that formula for curvature. Here we go. Find the curvature of a classic quadratic at x equals 1. So let's go get it. Get your fanciest k. A double derivative here just gives me 2. A curvature should always be positive. That's why you end up with all these things. And then here, I get 1 plus the first derivative, 2x squared, 4x squared, to the 3/2 power. And it says, hey, when is this thing, what is that curvature when x equals 1? Well, I would just plug in 1, 2 over 1 plus 4 to the 3/2 power. I mean, it doesn't get that much nicer. 2 over 5 rad 5 or 2 over square root of 125. I mean, they're the same thing, but they're not very nice. Sorry, I went off the page a little bit there when I plugged in the 1, but I believe you would follow me there. And a separate question, this is not necessarily a classic question, but you can maximize functions. You're capable of it. This is just a function. How do you find mins and maxes? You take a derivative. And then you make sure you find when that derivative is at 0, and you find when it's crossing from positive to negative. So let's take that derivative of the curvature. I would call this k prime. K prime, well, how about this? Original k is 1 plus 4x squared to the 3/2. When I go to d dx, this guy, I would get 2. I would have negative 3/2. I would chain rule an 8x. And then I would just tick down that denominator, minus 1, negative 5/2. Whew! Now that is a nice function. When I simplify this thing out, the 2, I get negative 24x over 1 plus 4x squared to the 5/2 power. How beautiful. In maxes, where does this thing hit? 0? The denominator is never going to be equal to 0. The numerator is the only thing that can be equal to 0. So negative 24x equals 0 when x equals 0. And now it's just my job to check, hey, is that numerator switching from negative to positive? It is. Or from positive to negative. Because that's what a max looks like when my slopes change from positive to negative. And that negative 24x is changing from positive to negative. And the denominator is always positive because it's a square root. So that means at 0, curvature finds its max. All right, folks. I'm going to leave it alone. I'm going to leave it alone. Have a lovely day. Goodbye.